Hi there. Not long ago, I wrote a book about how AI and large language models actually work. I felt a strong urge to really understand the topic, so I spent a lot of time studying and developing a solid understanding, which eventually became a book. The following podcast discusses the book. The book itself is not AI generated, but this podcast and the video you've just watched of me are. Nevertheless, I believe it offers an excellent summary of the book. So if you're interested in this topic, please give the podcast a listen. A link to the book can be found in the description below. I hope you enjoy it.
Welcome to the Deep Dive, where we take the complex and hopefully make it comprehensible. Today, we're diving into something that has completely reshaped our world. Large language models.
LLMs.
Right. We're pulling back the curtain on tools like ChatGPT and Claude, which can feel, well, they can feel a lot like magic.
They really can. And that feeling of magic is what we're here to dismantle. Our mission for this deep dive, drawing from Roger Gullhog's fantastic book, The Inner Workings of Large Language Models, is to show you the pure engineering underneath it all.
To understand the mechanism, not just get wowed by the effect.
Exactly. And Gullhog's own journey is pretty remarkable. He's the director of development at Rambase, and he basically set out on this personal quest to figure it all out.
Okay, let's unpack this. What is that one fundamental concept that everything else is built on?
It's just predicting the next word.
That's it.
That's it. Or, to be more technical, the next token. You give it some text, and the LLM just calculates the most probable next piece of text. Then it does that again and again, millions of times.
It's funny you say that because watching the text appear so slowly on the screen, that's not just for dramatic effect, is it?
No, not at all. That slowness is a literal window into the massive amount of math it's doing for every single one of those words.
So for that math to even start, you have a huge problem. Neural networks don't speak English. They speak numbers.
Precisely. You have to convert language into something computable, and that starts with a process called tokenization.
Which is basically just chopping up the text.
Yep. Splitting into tokens, words, subwords, whatever. Then each token gets a unique number, an ID, from a huge lookup table called the vocabulary.
But what happens if I type in a word the model's never seen? Some crazy long word or a brand new piece of slang?
Ah, that's the really clever part. It uses something called byte pair encoding, or BPE. Instead of just failing, BPE breaks down the unknown word, like unhappiness, into smaller bits it does know.
Like unhappy and less.
Exactly. So it can handle literally any text you throw at it.
Okay, so now we have numbers, a list of token IDs. But those are just labels, right? They don't have any actual meaning yet.
Right. And that brings us to the next crucial step, embeddings. This is where each of those simple number ideas gets mapped to a huge list of other numbers, a high-dimensional vector.
And when we say high dimensional, we're talking, what, a few dozen?
Try 12,000, or even more for the biggest model.
12,000.
Yeah.
That's impossible to even imagine.
Yeah.
Why so many for just one word?
Well, think about the word apple. It needs a dimension for its relationship to fruit, sure, but also to technology, to New York, to the color red, to health, to gravity.
I see. Each dimension maps a different potential relationship or concept.
You got it. That massive space lets the model create this incredibly rich map of meaning, but there's still a problem.
Okay. Right now, the model has a bag of words with rich meanings, but dog chases ball looks numerically identical to ball chases dog. It has no concept of order.
So how do you add the concept of order to a system of independent vectors?
You add another vector. It's called a positional embedding. It's just a vector that encodes the token's position, first, second, third, and so on, and you literally just add it to the word's meaning vector.
So the final input vector knows both what the word is and where it is.
Exactly. Problem solved. Now the model knows the meaning and the order.
Okay, but here's where it gets really interesting for me. A sentence is more than a list of words in order. It's a web of connections. How does the model figure out what it refers to in a sentence?
That is the magic of the attention mechanism. This is the core of the transformer architecture. The model needs to resolve that exact kind of ambiguity.
And it does this with those query key and value vectors I've read about. Yep. For every single token, the model creates 3 new vectors. The query is the token asking, what am I looking for? The key is every other token announcing, here's what I have to offer. And the value is the actual substance, the information.
So the query from the word it scans all the keys in the sentence, finds a strong match with the key for system, and then pulls in that value.
That's a perfect way to put it. The alignment between a query and a key creates a high attention score, and that tells the model where to focus.
And there's a special version of this for when the model is writing, right?
Yes, and it's absolutely crucial. It's called causal attention. It uses a mask that literally stops the model from looking ahead in the sentence. It can't see future tokens.
Why do that? Why blind it during training if the whole sentence is right there?
Because if it could see the future, it would just cheat. It would learn to copy the answer. The mask forces it to learn to predict the next word using only the words that have come before, which is exactly what it has to do when it's generating a response for you in real time.
And since one attention pass might only focus on one thing, like grammar, you run lots of them at once. Multi-head attention.
Right. A big model might have 64 different heads running in parallel. One's looking at syntax, another's looking at sentiment, another's tracking who's who. Then it bundles all those insights together into one super rich context vector.
So this vector now knows everything: meaning, position, and all its relationships. And this is where we get to the core computational engine, the transformer block.
The transformer block, it's just that attention mechanism we described, plus another piece called a feed-forward block, and this whole unit gets stacked, one on top of the other. GPT-3 has, what, 96 of them?
96 layers. Wow. But before we get to the feed-forward part, you mentioned layer normalization. It sounds kind of boring, but it's important.
It's critical. Imagine you have a signal passing through 96 amplifiers. Without a regulator, that signal would get distorted into useless noise very quickly. Layer normalization is that regulator. It resets the mathematical properties of the vector at every single layer, keeping the whole system stable and allowing it to learn effectively.
So it stabilizes the signal, and then that signal goes into the feed-forward block. What happens there?
The feed-forward block is where the token gets to think by itself. Attention was a group discussion, integrating context from all the other words. The feed-forward layer takes that contextual summary and processes it independently for each token. It's a moment of introspection, refining the information before passing it up to the next layer.
And after going through dozens of these blocks, you have a final, super refined array of vectors. How in the world does that turn back into a word we can read?
Okay, so the model takes that final vector and compares it against every single token in its entire vocabulary, tens of thousands of them.
A massive comparison.
A huge one. And that comparison spits out a raw score for each possible next word. These are called logits.
But a raw score isn't a probability.
Not yet. That's the job of the softmax function. It takes all those messy logits and squishes them down into clean probabilities that all add up to 1. Now, the model has a perfect probability distribution for every possible next word.
And then it just picks the one with the highest probability.
Well, it can. That's called greedy decoding. But it's really boring and repetitive. To get creativity, you need to use sampling.
And that's where you get controls like temperature.
Exactly. Low temperature makes the model confident and deterministic. It'll mostly pick the top choice. Crank the temperature up, and it gets more creative, more willing to take a chance on a less likely but more interesting word.
There's also top sampling, right?
Right, which is a nice balance. It creates a short list of the most likely candidates that add up to, say, a 90% probability, and then it samples randomly just from that pre-approved list. It keeps things creative but prevents it from going completely off the rails.
So we've built a fluent text generator. But a raw base model isn't very useful, is it? It knows language, but it doesn't know how to follow instructions. How do you turn it into a helpful assistant?
That is the critical jump from pre-training to fine-tuning. Pre-training is where it learns the rules of language by reading the internet. Fine-tuning is where it learns behavior, how to be helpful, how to answer questions, how to follow instructions.
And that involves a technique called loss masking. What's that?
Well, in fine-tuning, you feed it perfect examples, an instruction, and the ideal response. Loss masking tells the model to only calculate its error, its loss, based on the response part. It ignores the prompt.
So it's not learning to predict the prompt. It's laser focused on learning how to generate that perfect answer.
You got it. It's training for a specific job.
Fine-tuning a model with 175 billion parameters sounds astronomically expensive.
It used to be, but now we have techniques like low RF, low-rank adaptation. Instead of retraining all 175 billion weights, low RF freezes the original model and just adds a few small trainable layers on top.
So you might only be training a few million parameters instead of billions.
Exactly. It's a massive reduction in cost and time. It's democratizing the ability to specialize these giant models.
Okay, let's shift gears a bit. If these models are just predicting the next token, How do they appear to reason? How do they solve logic problems?
It's an emergent property. The model doesn't have an internal monologue. It has to think by writing. When we prompt it with a chain of thought approach, we're just training it that the most probable sequence of tokens for a hard problem is one that includes the step-by-step reasoning.
So all the thinking is happening right there in the text it generates.
Every bit of it, token by token.
This brings up a question I think a lot of people have. If I'm in a chat and I correct the model, is it actually learning from me?
And the answer, very clearly, is no. This is the no learning during inference rule. Your conversation happens in a temporary workspace called the context window. As soon as that conversation is over, that knowledge is gone. No weights are ever updated.
So if I want my LLM to know about my company's internal documents, what are my real options?
You basically have three. You can do that very expensive fine-tuning we talked about. You can stuff the info into the prompt, which is temporary. Or the most common solution now, you use RAG.
Retrieval Augmented Generation.
Right. RAG connects the LLM to an external database. When you ask a question, the system first retrieves the relevant facts from your database, injects them into the prompt, and then the LLM answers based on that fresh, verifiable information.
That seems much more efficient and safer than changing the model itself.
It is. It's the standard for enterprise use right now.
Which brings us to the big paradox Gullhag talks about in his book. We seem to understand all the pieces, the math, the architecture, but do we really understand how it works?
That's the billion-dollar question, isn't it? We know how it's built perfectly, but the knowledge isn't stored in one place. It's distributed across trillions of parameters.
He uses that analogy of trying to find a fact by fiddling with 1,000 knobs on an old radio.
It's a perfect analogy. You can't point to one parameter and say, that one stores the capital of France. The knowledge only emerges from the interaction of all of them. It's what makes the model so powerful at generalizing, but it's also what makes it so hard to audit.
And that general capability is pushing LLMs way beyond being simple chatbots.
Oh, absolutely. We're moving toward the LLM as a universal interface. They're being given tools to control software, to call other AIs, to orchestrate complex workflows just from a simple instruction in plain English.
Like Gullhag himself did, using the AI as a collaborator to help him write the very book we're discussing.
He literally used it as his developmental editor. He'd feed it chapters and ask it to critique the structure, check for clarity. It shows you that the AI is becoming a necessary partner, even for the experts.
A tireless, patient tutor and collaborator.
It really is. So I guess that leaves us with a final thought for you to chew on. If the model's knowledge is truly distributed like those 1,000 radio knobs, and we can't just look inside to verify a fact, what does that mean for trust? For debugging? And how does our role as human fact-checkers change when the AI can now literally show its work step by step?
It forces us to redefine what we mean by knowing something. An amazing place to end. Thank you for this deep dive into the architecture of these incredible systems.
It was a pleasure. The book goes into so much more detail. It's a fantastic resource.
If you want to learn more, see a link to the book in the description below.